Welcome to the lesson on magnetic inspection tools. By the end of this lesson, you will be able to explain the principles of eddy current inspection and interpret how material properties influence its response. You will be able to describe the working principle of magnetic particle inspection and identify the types of discontinuities it can detect. In addition, you will differentiate between circular and longitudinal magnetization methods and evaluate the effective flux density, including comparing continuous and residual magnetization techniques. Finally, you'll be able to describe magneglow inspection, magnetizing equipment, and the purpose and methods of demagnetization. Let us begin with eddy current inspection, an electromagnetic method used to detect defects in conductive materials. Eddy current inspection is a non-destructive technique that uses electromagnetic principles to evaluate conductive materials. When alternating current is applied, it induces electrical currents within the material without requiring physical contact. These currents respond to changes in the material, allowing detection of surface and subsurface defects. Because there is no direct contact required, this method is especially useful for inspecting coated surfaces such as painted or anodized components, making it highly practical in aircraft maintenance. Building on this concept, let's look at how eddy currents behave inside the material. Eddy currents are circulating loops of electrons induced by a changing magnetic field. The inspection probe introduces this field into the component. The flow of these currents depends on material properties such as electrical conductivity and magnetic permeability. Any variation in these properties, such as a crack or corrosion, disrupts the current flow. The instrument detects these changes, allowing technicians to identify potential defects accurately. Now let's examine the working principle in more detail. When alternating current flows through a coil, it generates a changing magnetic field around it. As illustrated in the diagram, this magnetic field penetrates the material and induces eddy current. These currents create their own opposing magnetic field, which interacts with the original field. This interaction changes the impedance of the coil. By measuring these changes, the instrument can detect defects such as cracks or heat damage, even if they are not visible on the surface. When a discontinuity is present, it disrupts the flow of eddy currents and alters the electromagnetic response. These changes are measured as variations in impedance and displayed as signals on the instrument. As seen in the image, technicians interpret these signals to identify defects. One key advantage is that inspection can often be performed without removing coatings like paint, allowing faster and more efficient inspection. Let's look at where eddy current inspection is applied. This method is widely used to detect cracks, corrosion, heat damage, and variations in material properties. It is commonly applied to turbine components, wing skins, wheels, bolt holes, and bores. The images on this slide show inspection on a crankshaft and a fan blade. It is also used in manufacturing to inspect castings and machine parts. Its ability to quickly and accurately detect both surface and subsurface defects makes it highly valuable. Let's now move to magnetic particle inspection, a method used to detect defects in ferromagnetic materials. Magnetic particle inspection method is used to detect defects in ferromagnetic materials such as iron and steel. It is particularly effective for identifying surface and near-surface discontinuities. It works by revealing the location, size, and shape of defects. Unlike eddy current inspection, this method cannot be used on non-magnetic materials. One of its key advantages is that it not only reveals the presence of a defect, but also helps indicate its location, approximate size, and shape, making it very useful for maintenance inspections. Let's look at how magnetic particle inspection actually works. The process begins by magnetizing the part using an external magnetic field. Then, magnetic particles are applied to the surface either in dry or wet form. As illustrated in the diagram, when there is a discontinuity such as a crack, it disrupts the magnetic field and causes flux leakage. This creates opposite magnetic poles around the defect. The magnetic particles are attracted to these areas and gather along the discontinuity, forming a visible indication. This indication outlines the defect, allowing technicians to clearly identify its location and shape. Let's examine the types of discontinuities that can be detected. These include cracks, laps, seams, cold shuts, inclusions, splits, tears, pipes, and voids. These defects can originate from manufacturing processes or develop during service. Cracks and splits involve separation of the metal, while laps and cold shuts are formed due to improper metal flow during forming. Inclusions are foreign materials trapped within the metal. Each of these discontinuities can weaken the structure and must be identified to ensure the safety and reliability of aircraft components. Before performing inspection, proper surface preparation is critical. Any grease, oil, dirt, or other contaminants must be completely removed from the part. These substances can attract magnetic particles and create false indications or mask actual defects. Cleaning is especially important when using the dry powder method, where particles can easily stick to contaminants. Small openings and oil holes must also be sealed to prevent particle accumulation. Proper preparation ensures that the indications formed during inspection accurately represent real discontinuities rather than surface contamination. Now let's focus on one of the most important concepts in magnetic particle inspection, which is flux direction. Magnetic flux lines represent the direction of magnetic force within the part. As shown in the diagrams, defects are best detected when the magnetic field crosses them at approximately a right angle. If the field runs parallel to the defect, it may not produce sufficient flux leakage and the defect can go undetected. Since defects can exist in multiple orientations, the part must be magnetized in more than one direction. This ensures complete inspection coverage and improves the reliability of defect detection. Building on flux direction, let's look at the two main types of magnetization. As shown in the images, circular magnetization is achieved by passing current through the part, producing magnetic lines that encircle it. This method is effective for detecting defects that run parallel to the axis of the part. Longitudinal magnetization, on the other hand, is produced by placing the part in a coil or solenoid, creating magnetic lines along its length. This method detects defects that run across the axis. Using both types ensures that defects in all orientations are detected. Now let's discuss flux density and how indications are interpreted. Flux density refers to the strength of the magnetic field applied to the part. Increasing the field strength improves sensitivity by enhancing the formation of indications at discontinuities. However, excessive flux density can produce false indications such as patterns caused by the material's grain structure. Indications are evaluated based on their shape, width, buildup, and sharpness. Clear and well-defined indications typically represent surface cracks, while less distinct patterns may indicate subsurface defects or non-relevant conditions. Let's now compare the two magnetizing methods used in practice. This builds directly on how field strength influences sensitivity and detection capability. In the continuous method, the part is magnetized while the indicating medium is applied, which ensures maximum flux density at the time of inspection. This allows detection of very small and subsurface discontinuities because flux leakage is strongest under active magnetization. In contrast, the residual method involves magnetizing the part first and then applying the indicating medium after the current is removed. This method relies on retained magnetism in the material, which results in lower sensitivity. The continuous method is therefore preferred for critical aircraft components where higher accuracy is required, while the residual method is used when sufficient residual magnetism exists and high sensitivity is not necessary. Let's now examine an advanced variation of magnetic particle inspection, the MagneGlow inspection. MagneGlow inspection method builds on standard magnetic particle inspection by enhancing indication visibility. This method uses fluorescent magnetic particles that are viewed under black light in a controlled, darkened environment, as shown in the image. When these particles gather at areas of flux leakage, they emit a bright glow, making even very small discontinuities clearly visible. This significantly improves detection sensitivity compared to standard visible particle methods. It is especially useful for inspecting precision components such as gears, threaded parts, and engine components, where small defects can lead to failure. After inspection, the part must be cleaned to remove the indicating medium and demagnetized to eliminate residual magnetism before returning to service. Now that we understand inspection methods, let's examine the equipment used to perform them. Equipment selection directly affects how magnetization is applied and controlled. Fixed general-purpose units are designed for controlled inspection environments and provide both circular and longitudinal magnetization. These units operate using either AC or DC current, depending on inspection requirements such as depth of defect detection. Contact heads are used to pass current through the part and securely hold it in place for circular magnetization. A solenoid is used for longitudinal magnetization. The system also includes a pump that circulates and applies the magnetic particle suspension to the part, ensuring uniform coverage and consistent inspection conditions. Portable magnetizing units are used to inspect large or installed aircraft components directly on the aircraft. These units supply both AC and DC current and use flexible cables with prods or clamps to apply magnetization. Circular magnetization is achieved using prods or clamps, while longitudinal magnetization can be achieved by wrapping the cable around the part. These units do not support the part physically, but provide the necessary current for inspection. They are particularly useful for inspecting landing gear, engine mounts, and structural components in service. When using portable equipment, different methods are required to apply current effectively. This leads to the use of prods in situations where clamps are not practical. Prods are used when it is not possible to place clamps on both sides of a part, especially for large or flat structures. Prods are held against the surface to introduce current directly into the inspection area. Proper contact is essential to ensure a consistent current flow. Because high current is used, there is a possibility of slight surface burning at the contact point. However, with correct handling and firm placement, this effect can be minimized. In many inspection scenarios, slight surface burning is considered acceptable when using prods. The effectiveness of inspection depends heavily on the properties of the indicating medium. Magnetic particle inspection uses indicating media in either wet or dry form. Wet methods use particles suspended in a liquid, while dry methods use fine powder applied directly to the surface. These particles are often colored or fluorescent to improve contrast and visibility. For proper performance, the particles must have high permeability so they are easily attracted to flux leakage, and low retentivity so they remain mobile and do not cluster together. These properties ensure that particles accurately outline discontinuities without forming false indications. After inspection is completed, it is essential to remove any remaining magnetism from the part. Demagnetization is the process of removing residual magnetism that remains in a part after magnetic particle inspection. This step is essential before returning the part to service because retained magnetism can attract metallic debris during operation and interfere with sensitive components or instruments. Demagnetization is achieved by applying an alternating magnetic field whose strength is gradually reduced. This is typically done using AC current through a solenoid coil, which creates a reversing magnetic field that progressively randomizes the magnetic domains in the material. As the part is slowly moved through and away from the coil, the magnetic field strength decreases, reducing the residual magnetism. Portable units can also perform demagnetization by passing alternating current through the part and gradually reducing it to zero. To ensure that demagnetization is effective, proper technique and handling must be followed. Effective demagnetization depends on correct equipment selection and proper procedure. The solenoid used should be appropriately sized to ensure the part is fully exposed to the magnetic field. Smaller parts should be positioned close to the inner wall of the coil, where the magnetic field is strongest. Parts that are resistant to demagnetization should be moved slowly through the coil and may require rotation or tumbling to disrupt magnetic alignment in all directions. It is important to continue moving the part away from the coil until it is well outside the magnetic field. Cutting off the current too early while the part is still within the field can result in the part becoming magnetized again. Let us now summarize what we have learned in this lesson. Eddy current inspection uses electromagnetic induction to detect defects in conductive materials by analyzing changes in current flow. Magnetic particle inspection is used to detect surface and near-surface defects in ferromagnetic materials. Proper surface preparation and correct flux direction are essential to ensure accurate detection of discontinuities. Circular and longitudinal magnetization methods are used to detect defects in different orientations. Flux density must be carefully controlled to achieve proper sensitivity without creating false indications. The continuous method provides higher sensitivity compared to the residual method. Magneglow inspection enhances defect visibility using fluorescent particles. Proper selection of equipment and indicating medium ensures reliable inspection results. Demagnetization is required to remove residual magnetism and prevent operational issues. Thank you for your attention.